Solve for the law of the wall, we need to know what this term z naught is. I mentioned that it's a roughness length, but what does it actually mean, and how can we solve it in terms of things that we can actually measure? So we can first think about how the roughness is interacting with the flow. And so the value of z naught is going to depend on whether the flow is hydraulically smooth or hydraulically rough. And what does this mean? So I mentioned that there is a laminar sublayer, and what hydraulically smooth means is that the height of the roughness, so I'm going to say, I'll just say, what letter should I use? I'll just write it out. Of roughness elements is less than the height of the laminar sublayer. And then in corollary, hydraulically rough means that this is greater than the height or thickness of the laminar sublayer. So I'll just write this. So let's go back to the Reynolds number, and we're going to define a Reynolds number down here, which is the boundary Reynolds number. So what is the Reynolds number near the boundary? And so based on Nicorazzi's data, and we can, if you're really interested, you can go back to these original papers that he wrote on roughness and pipe flows. Hydraulically smooth flows occur for boundary Reynolds numbers that are less than 3, and hydraulically rough flows occur when that Reynolds number is greater than 100. And of course, there's a transition zone that's really messy in between those two. And based on equation 22, the equation, let's cross that out and be grammatical. Unless, I was from Southern California, it could be, the equation, just like the highway. So from equation 22, you can calculate a roughness length, Ks, is a function of grain size, d. And in particular, I'm just going to remind you that K sub s, this roughness, is approximately equal to 3.5 times D84. So these are the larger grains, right, the 84th percentile. So if you're in the 84th percentile in a class, you're probably getting a pretty good grade. You're not at the top, but that's okay because the world doesn't think you're some kind of uber nerd, and you're certainly not at the bottom either. So D84 is up here, and so this is 84th percentile grains. And we use the D84 because it's these larger grains that are really protruding into the flow and causing a lot of the roughness. So we can calculate this boundary Reynolds number as U sub tau. So remember that this is going to be equal to, in steady uniform flow, square root of GHS times K sub s, which is going to be given by this, over the, kinematic viscosity. And the kinematic viscosity is mu over rho. Mu is 10 to the minus 3. Rho is 10 to the 3, and these are in SI units. And so therefore, mu over rho is going to be 10 to the minus 6. And this has units of, of meters squared per second, which is similar to any kind of diffusivity. So from this, we can define this Z naught term, or Z naught, because I'm American, even if you don't know it from how I talk occasionally. And for hydraulically smooth flow, Z naught, so we can, and once you calculate this, for hydraulically smooth flow, you have this relationship for Z naught that's just related to the viscosity. And that's because all of these small stones or roughness elements on the bed are all, nicely under a little, like gently undulating sheet of flow where that all has a laminar velocity profile. And so there's just viscous drag between the bed and the flow. But pretty much all natural rivers are hydraulically rough. I'll leave you to go through this exercise and figure that out if you so choose. But what that means then is that we have something like these roughness elements, and the laminar sublayer is really thin and just barely, kind of clinging to them. And so what that means is that there's turbulent flow that's creating eddies in between the grains. And that turbulent flow then means that the Z0 is going to be controlled by this roughness length scale. You can think about that as similar to these eddy length scales. We have that divided by 30. That's just empirical data. And so if I look at something like this, I can then pop in, this thing where this is about 3.5 times D84. And at the end of the day, I might be going through all this physics, but I'm really a geologist. So if we have Z0 is equal to 3.5 D84 over 30, I'm just going to say 3.5 is pretty close to 3, and it's a lot easier to divide by 10, right? Just take the D84, move a decimal point. It's something I can do in my head in the field. So let's just call that about D84 over 10. And I'm happy because my mental math doesn't have to be too hard. And for those who are interested in any further reading, these relationships are based on the experiments by Nicorazzi in 1933. And believe it or not, yes, we have that in the references list. Sorry that it is in German. For those of you who might be in the College of Liberal Arts, this might be your chance to use your foreign language skill. So, as a summary of everything then in this section that goes beyond just talking about the grain size and the roughness right here, so far we've computed flow and shear stress within an open channel for both laminar and turbulent flows, hopefully gain some insight into how viscosity and momentum affect the form of flows, and become familiar with some of the standard equations and terminology used with open channel flows. So using this as a starting point, we are now going to graduate from this open channel hydraulics section and move back into the natural system and think about rivers and how sediments move and landscapes evolve, interact with the surrounding hill slopes, and change the world around them. So with that, we close this section on flow mechanics.